Welcome back to the Geometry Control Room. We're in the final stage of our series, where we'll use the rules we've gathered to solve complex multi-line puzzles and see how geometric logic can override visual deception. Look at these highlighted angles tucked snugly between parallel lines on opposite sides of the transversal, alternate interior angles. Watch the bottom angle slide up, matching its corresponding twin perfectly. Then it crosses the intersection to its vertically opposite position, locking exactly into our target. Because both of these logical steps are based on fixed geometric laws, we know that whenever a transversal crosses parallel lines, alternate interior angles must be equal. Now let's look at a different pair. These interior angles are on the same side of the transversal wall. While they might look similar at a glance, the math tells a different story. If we assume the angle outside our track is 50 degrees, its neighbor on the straight baseline must be 130, because linear pairs always add up to 180. That 130-degree angle then jumps down to its corresponding spot on the lower parallel line. Now, look at our two interior angles together. 50 degrees plus 130 degrees equals 180. This reveals a consistent property. Interior angles on the same side of a transversal are supplementary, meaning they will always sum to exactly 180 degrees. Let's apply these rules to a more complex layout. We have three parallel lines, AB, CD, and EF, along with a perpendicular drop on the left and a diagonal transversal on the right. Your first task is to find angle Y. Pause the video here and see if you can calculate it using the same side interior rule we just covered. If we narrow our focus to just the bottom two parallel lines, we see that Y and 55 sit on the same side of the transversal. Subtracting 55 from 180 gives us a value of 125 degrees for Y. To find ATS, we look at the top. Because the vertical line is perpendicular to AB, it creates a 90-degree corner. And since AB is parallel to EF, that entire corner at the bottom must also be a right angle. The transversal takes up 55 degrees of that 90-degree space. Subtracting 55 from 90 leaves us with 35 degrees for X. By isolating specific pairs of lines and dimming the rest of the diagram, even the most crowded geometric problems become simple to solve. Take a look at these two vertical lines. Do they look perfectly straight to you, or do they appear to be curved or bent? Your brain is being tricked. Because the background lines intersect the vertical ones at sharp angles, your visual cortex exaggerates those intersections, making it look like the lines are bowing outward. Dropping a mathematical grid over the image reveals the truth. The lines are 100% straight and parallel. This is why we rely on geometric proof and measurement. Logic provides a clear answer, even when our eyes are being deceived. For our final challenge, we have a zigzag diagram. We know the top and bottom lines are parallel, but there is no single transversal to help us find the missing angle, NOP. In cases like this, we use auxiliary lines, extra lines we draw into the diagram to create the connections we need. By drawing a dashed line through the center point that is parallel to the others, we suddenly create two new transversals and a set of alternate interior angles that we can solve individually. Use this auxiliary setup to calculate the final value of angle NOP and share your answer in the comments. You've now mastered the core principles of parallel lines. Just remember, corresponding and alternate interior angles are equal, while same-side interior angles always sum to 180. Thanks for joining us for Chapter 5.